Cool. Hello, my name is Craig. In this video, I'm going to go over the uh, Level 1 Physics, Earth and Space Science 2024 exam, just the question 2. And question 2 is about the thermal energy. So let's just get straight into it. It says here, Oliver wants to be able to keep his water cool the whole day while he is at school. Firstly, he tries freezing a bottle of water to take to school. Over the day, Oliver finds that it takes a long time for the ice to melt. Once the ice is melted, the water gets to room temperature quite quickly. And then we're given some figures here. We're given the specific heat capacity of water, and so that's the amount of energy is required to heat up water. Then you've got the latent heat of fusion. So latent heat of fusion is one of the questions. It's question A. And we've got the mass of the water in the bottle as being 750 milliliters, which is pretty much 0.75 kg or 750 grams. Okay, so the first question is, what does the term latent heat, latent heat of fusion mean? In this case here, latent heat of fusion is the amount of energy required to change state from solid to liquid or from liquid to solid without a change in temperature. So this would be the key answer. And so you could say either from solid to liquid or liquid to solid. And the idea of this is something akin to, if I can get this picture, the image, something you may have come across in class, possibly. It's going to work. Maybe not. Okay, maybe I'll just redo this. Oop. We got there, people. Cool. Yikes. Okay, so we've got a couple. So it did work, it was just being weird. Okay, cool. So when you heat something up, if you're trying to change it from a solid to a liquid, or even a liquid to a gas, you have to provide an extra amount of heat. You heat it up to a certain point. If it's water, you heat it, ice, let's stay with ice, you get it to 0 degrees Celsius, and then from there, all the extra heat that you're going to be pumping in is actually to change it from the solid state to the liquid state. And that's the latent heat of fusion. It's like it's a transition state of sorts. It's a change in state. It's a change in state. Calculate the heat energy required for 0.75 kilograms of water to change state from solid to liquid. And so this is where you get your formulas. In this case here, we use the nice simple formula of the energy multiplied by the mass. The energy equals the mass times the latent energy. In this case here, the energy required, or the heat energy required to change it from a solid to a liquid, or even from the energy you want to get it back out to get it from liquid back to solid is this equation here. So the capital L represents the latent heat of fusion, and little m is the mass, and you'll get something like this. You're allowed to, this is just an achieve tick. In this case, you're allowed to not have a unit, but I highly recommend always putting units. And you can just leave it in joules. Don't worry about changing it to kilojoules for this one. They've given you these figures at the top in joules as well. So if you just want to keep it in joules, keep it in joules. The temperature against time graph below shows what happens to ice when taken out of the freezer. Use the information provided opposite and the graph below to describe the reason why it takes a longer time for the ice to completely melt and a much shorter time for the melted water to get to room temperature. So we can see here what they're describing is a really long period of time. Let's see if I can do it. A really long period of time for it to melt compared to, look at how much time it's only, 1 hour for it to increase in temperature here and less here. So why does it take so long to melt? And the reason for that is to do with the figures that we saw above. That gives you a clue. I'll highlight these. So the specific heat capacity of water, that top one is to do with increasing the temperature of the water. or even the solid water, the ice. Where the latent heat of fusion, notice that it's a much bigger number. And so because it's a bigger number, the latent heat of fusion it requires so much more energy to get things done. Let's get that for you. And so if you put something like this into your exam, the specific heat capacity of water is much less than the latent heat of fusion because, okay, so if you just say which one's bigger, you get an achieve tick, congratulations. But then when you get to the explanation side of it, because the energy required to get particles moving faster is less than the energy required to change state. Changing state requires a lot of energy compared to just getting them moving around and vibrating around a little bit more. Cool. Oliver next decides to try using a thermos that holds the same volume of water as his earlier bottle. The thermos flask is also known as a vacuum flask. It is a double-walled glass vessel that is designed to minimize heat transfer by keeping hot things hot and cold things cold. Describe two key features of a thermos that reduce heat transfer and explain the type of heat transfer each feature is designed to reduce. Now, there's a lot of features on here, and you only need to describe a couple of them, only two of them. But you always want to relate them to the three different types of heat transfer. That's convection. That's where you have mass flow, like a fluid flow of some sorts, hot things actually physically moving somewhere else. Conduction, which is where heat is transferred along, like usually a solid piece of mass. That's what you would normally relate it to. If you have a metal fork, and you heat it one side, it gets hot across the fork. And then the last one is radiation. And in this example, radiation. Something wrong. Is that how it's spelled? Something feels a bit wrong. Yeah, radiation. Where in this case it'll be like infrared radiation that could be given off. Hot objects give off heat radiation. Even the Earth, as it's hot, it radiates some heat into outer space through the atmosphere, for example. So in this case here, we've got those three different types of heat dissipation that we could go for, and there are actually plenty of examples you can use from the bottle. The examples that they've given in the answer schedule, you can make a choice from. So we've got vacuum. So we've got the vacuum in the middle between the two glass layers to reduce heat loss via conduction and convection as well. Okay, because there's a vacuum, there's no particles in there, so you can't get conduction of heat. You can't get convection of heat because there's nothing in there. It's a vacuum. A reflective coating to reduce heat energy loss via radiation. So that reflects the heat back in. And so as long as you mention radiation of some sorts, there's a tick there. The stopper in the top is to prevent loss via conduction or convection. So if you didn't have the stopper, air could flow in and out, so there'd be a convection kind of thing. But you also have conduction of the air as well. So this stops particles passing on particle motion. So the liquid, he wants to keep it cold. He was trying to keep stuff cold before, I think, maybe. Okay, yeah. So if he wants to keep it cold, he doesn't want the heat coming from the outside and getting into the bottle. But you also go the other way as well. You want hot things to stay hot. And the last one is using glass. Glass is a poor conductor of heat. And so many of you may have come across the example of double-paned windows or double-glazed windows. So the same idea is being used in these thermoses where you've got you've got a vacuum in between the two glass layers, where in double-paned windows it's usually just air. Some fancy ones will have a fancy gas that's in there. Oliver decides to test his thermos and finds that at the start of the day the temperature of the water is 5 degrees Celsius. 5 hours later, he finds the temperature has risen to 12 degrees Celsius, show that the average rate of thermal energy absorption of the water in the thermos over the 5 hours is approximately 1.2 watts. And so in this case here, again, we've got an energy transfer, and in this we've got 1.2 watts, so watts is power over time. So we need to make sure that we're using there'll be at least two equations. One of them will be calculating the energy being transferred, and then the second one will be calculating the power of that energy transfer because it's being done over time. So we've got here, the rate of thermal energy can be calculated by using the total energy gained divided by the time taken. Okay, so we're going to be using the E equals mc delta T because we've got a change in temperature, we've got a mass, and then we've got the thermal, C being the thermal, the calories required essentially to heat up the water, because the water is being heated up over that time. Okay, the first instance to calculate the energy, let's look at that one first. We already know how much temperature and mass. They don't state the mass in this question, so in question E, but we know what the mass was from a previous question. We won't go up there because I've got the answer in here anyway. So the change in temperature in degrees Celsius is 7. That's the change in temperature. We're going from 5 to 12. So 12 is the end and 5 is the initial. 12 minus 5 is 7 because we're increasing in temperature. Mass is 0.75 kilograms, and then to heat up the water it's 4,200 joules per kg per degree Celsius. And so we can calculate the energy required. And in this case, you can, if you so wish, use standard form. It's not wrong. That's what they're saying in terms of they'll accept it. That's fine. So this is okay and this is okay. But the problem you'll come across if you use this kilojoules one is that you do not want to use kilojoules in your next equation to calculate your power. Because if you do, it will not come out right. So I would kind of discourage using kilojoules. It's up to you though. It's up to you. Because it may mess up your next calculation to calculate the power, which is this one here. So to calculate the power, you put the energy on top. So this power calculation comes from formula, where's my pen there? Formula that goes P equals delta E over T. So we've got the delta E up the top, change in energy, and we've got the time because we're doing 5 hours times 60 minutes. So for every 5 hours, there's 60 minutes. For every minute, there's 60 seconds. And so it's 5 times 60 times 60 to get your, actually, how many seconds would there actually be? 5 times 60 times 60, 1,800. That's how many seconds it is. Sorry, 18,000 seconds. And then we've got our 22,050 joules. That works out to be approximately 1.2 watts. Which again, with these questions so far on this exam, they've always given you the final answer and they want to see how you're working it out. They want to see you're working. That's kind of the key thing. Is that it for thermal energy? It is. Then we get on to electricity. Fantastic. The next video will be on electricity then, my favorite subject.